Dishwasher being installed in mostly in Europe right now, and it's a 1 kilowatt electric unit. Kind of the state of micro CHP. There's a few different areas that they're looking at for how they're going to generate electricity and heat. Internal combustion engines, or ICEs, external combustion engines, such as the Stirling engine, and that gets all the heat stinking. Mechanical engineers always wanted to do something with Stirling engines. And small turbines, such as pico turbines and these organic Rankine cycle systems, and fuel cells. I'll talk about internal combustion engines, Stirling engines, and fuel cells here. So the Stirling engine, if you don't know, it's an external combustion engine. So that means the heat is applied to the external to the cylinder using like a gas burner. Typically low electrical efficiency, 10 to 15%. But they're very quiet operation, small footprint. That little unit that is a residential unit is the size of a dishwasher. It's meant to incorporate into your kitchen or mechanical room. Really, they're targeting the replacement boiler market in Europe and the UK. And Whispergen is a company who has a market-ready solution, and they're going great guns in Europe right now. Internal combustion engines, kind of more of a recent development. They've been developed for long life and a really long service interval by putting large oil sumps and that kind of thing in. There's many sizes available, all the way down from a 1 kilowatt. Honda developed a system that's a little internal combustion engine, that's 1 kilowatt output, up to over 500 kilowatt of electric output. They have higher electrical efficiency than a Stirling engine, typically 20 to 30%. Recent developments include they've really improved the emissions ratings and increased the service life. There's units out there with a 10,000 hour service life. Marathon, Yanmar, Honda Freewatt, Baxi, and others have all developed these internal combustion CHP products, and they're available on the market. Fuel cell CHP, this is really just in the development stage. I don't have any good pictures of any of these things because they're all boxes. That's how the people, their market is. They look like a boiler. They're in the development stage, but they show great promise because they have really high electrical efficiency, upwards of 40%. And there's two kind of technologies you're looking at: proton exchange membrane and solid oxide fuel cell. I'm not going to get into the details of those, but what's important to know is that the performance of these fuel cells degrades over time. It's similar to like a battery. They have very high cost right now, but what's really promising is that the thermal output is really close to the electrical output, which really helps in sizing, which I'll get into in a little bit. And with CHP, you definitely want to run the system as much as possible to get the benefit to the building owner and to the environment. So really, North America is kind of behind times in terms of CHP adaptation. From 1993 to 2009, there was almost 4,500 megawatts of CHP technology installed in Japan, with over 6,000 commercial units. I know of 2 in Canada right now, one of them is ours. There's over 30,000 micro CHP units installed in Germany, and it's really being seen as a viable replacement technology for boilers in Europe and the UK. Very little market uptake in North America, and I think that's mostly because we have forced air systems. We're not a boiler society, and there's really low availability because manufacturers haven't brought their products here yet. So some of the new developments, we have lower equipment costs and increased number of products in the market. Even in the time we did our demonstration, 3 manufacturers were able to come into North America. We have grid parallel operation and this off-grid operation, so the unit can run as a backup generator. When we started our demonstration project in 2008-2009, there was no market-ready products available in Canada that met any regulatory requirements. Since then, 2 have come on, the Marathon and Yanmar in the commercial size, and Honda Freewatt has also come in the residential. So the potential benefits are really seen in terms of reduced source energy. So a combined heat and power system to produce the same amount at your load of electricity and heat requires 37% less input energy than buying electricity from the utility and running your natural gas furnaces. It also can show that greenhouse gas emissions can be reduced by almost 50%, like 47%, compared to a high efficiency boiler and purchased electricity from the grid. Which is kind of why we started looking at this technology. We see it as a promise for reducing greenhouse gas emissions, as well as people always want to have that autonomous nature in their buildings where they have that backup power and they produce their own power. The applicability to Saskatchewan. Sask Power's peak electrical demand takes place in winter months, which is great. That's when these systems will be operating. Saskatchewan has a high reliance on coal-fired power, so it's very greenhouse gas intensive. If you're going to make a benefit to Canada in terms of reducing greenhouse gas emissions, Saskatchewan and Alberta are great places to do that. As well, over 90% of Saskatchewan residences and businesses are connected to the natural gas network. So we have that infrastructure available to install these things and deploy them. CHP systems can run as power backup. There's lots of rural communities where power outages are they're a reality. And people need some way to produce their backup power. And yeah, like I said, we're a cold climate, well suited for this technology, and should be able to maximize benefits. So our demonstration project we did down in Regina, we tried to source a micro CHP unit in the 5 to 10 kilowatt electric range. We wanted to demonstrate the technical performance, how efficient is it, and what kind of barriers are there to the installation of this system. This is new technology to Canada, definitely new to Saskatchewan, and the code officials don't know how to deal with it, the building owners don't know how to deal with it, utilities don't know how to deal with it. So we wanted to go through, document how we installed it, where we felt there was barriers, and how we can overcome those. As well, we wanted to evaluate the overall performance. Is this really a winning technology? And we need to better understand the economics and the environmental impact. Findings from this program are going to help everybody involved to develop how they're going to process these systems in the future in terms of incorporating them into codes, providing incentives for early adoption, that kind of thing. So we couldn't purchase what we wanted at the time, so we built it. We commissioned Advanced Engine Technologies out of Ottawa. They have a lot of experience in building engines and converting engines over to natural gas, as well as adapting heat exchangers. They developed some other combined heat power systems in the past, and we really felt like they had a good value proposition for us. They used as many commercially available components as possible when they developed this unit. It's actually a Cummins-Onan diesel generator they converted to run on natural gas, added in heat exchangers, built in some components for longer service life, and added in some extra electrical generation systems. What's kind of unique features about the system, and it's still even unique to this day, is that the system can run in parallel with the grid, so you're using power and exporting power back to Sask Power. Or if the power grid goes out, the system clicks over and supplies power to an essential service panel in the building. So if you had something like your data center that you needed to keep power on, this system would be able to do that. System is capable of high overall thermal efficiency, considering they developed it in less than a year, and also capable of starting down at minus 35 degrees Celsius, which is important in Saskatchewan. From a mechanical perspective, when you're installing or thinking about CHP, some of the important things, system life is typically 35 to 60,000 hours. Prior to, you have to do a complete rebuild on the engine or the system. Some of the larger scale CHP manufacturers have 15 to 20 year guarantees, so that kind of gives you an idea of when the system would have to be replaced or overhauled. The system's sized to maximize runtime, so you don't put in, if you needed 100,000 BTUs worth of heating in your building, you wouldn't put in a 100,000 BTU CHP plant. You would put in something that's smaller that can handle the base load. Because you want that system running as many hours in the year as possible to maximize the economic benefits. And the CHP unit is implemented as a first line of heating, so it would work in conjunction with your existing boiler or furnace as providing that base load of heating and letting your existing system do the peaking if needed. And that's where I think the big difference is between Europe and here, is that in Europe they can take these units and they can replace the boiler. Whereas here, they have to be in addition, like a solar thermal system or solar PD, that kind of thing. From an electrical perspective, You want to try and use as much of the power in-house as possible, depending on programs and rates and that kind of thing. But it's also not economically feasible to run the system just for power generation. If you're not using the heat,